Hi students, now we are going to discuss the motion of a charged particle in a uniform magnetic field. So for that, let us assume a uniform magnetic field B whose direction is into the board. Okay, so these X marks are the lines of force are passing into the board perpendicular to the plane of the board. And I am going to consider a charged particle Q which is moving in a direction perpendicular to the magnetic field. So that here theta is equal to 90 degree. Okay, theta is equal to 90 degree. That means the charged particle is perpendicular to the magnetic field. So we have studied that when the charged particle moves perpendicular to the magnetic field, it experiences maximum Lorentz force. Okay. Now Q is the charge of the particle. So I will consider Q is the charge of the particle and M is the mass of the charged particle. V is the velocity of the particle, and when it moves in a circular path, here the radius of the circle is denoted by small r. So this is the diagrammatic representation, and here what we are going to derive is the period of revolution of the charged particle, the time taken by the charged particle to revolve once in a circular path, that is called the period. Then the reciprocal of the time period is called the frequency of revolution. Okay, so we are going to derive expressions for the time period and the frequency of revolution of the charged particle inside a uniform magnetic field. So now we start with the expression for the Lorentz force. Okay, first I will write an expression for the Lorentz force, which is given by F M is equal to Q into V cross B. Okay, V cross B. So this is also equal to Q V B into sine theta, that is sine 90. So sine 90 is equal to 1. Therefore the magnitude of the Lorentz force is Fm is equal to Q into V into B. So this is the magnitude of the Lorentz force equation 1. With this force, now the charged particle is moving in a circular path of radius r. So I will consider that it is revolving in a circular path of radius r, so that it experiences a centripetal force. So the centripetal force is given by centripetal force is equal to mv square by r. So F centripetal, the magnitude of the centripetal force is equal to mv square divided by r. This is equation 2. So these two forces are going to balance each other. Therefore I will write therefore Q into V into B is equal to mv square by r. So in this equation, V square power 2 is getting cancelled with velocity V on the left side, and I will bring the r term to the left hand side. So left hand side I will bring r. So r is equal to m into V divided by BQ. So mass into velocity in the numerator. That is also equal to the momentum. So P divided by BQ. Or I am going to modify this equation like this. This r divided by velocity. So r divided by velocity V is equal to m divided by BQ. M divided by BQ. And this is a required equation for the further steps. So I am calling this as equation 3. The ratio of r by V is equal to m divided by BQ. Now you see here the ratio of the radius of the circular path to the velocity of the particle is a constant, because mass of the particle, charge of the particle and the strength of the magnetic field all are constants. So r by V is a constant, or V by r is also a constant, you must remember. Okay. Now in a circular path, the time taken by the charged particle to complete one revolution is called as period of revolution. Okay, period of revolution is given by capital T is equal to the distance traveled in one circular path, that is the circumference 2 pi r divided by the velocity v. So this is now equal to 2 pi into r by v is there, you see, r by v, is it not? So this in a bracket I will write r by v. I am going to substitute for this r by v from the equation 3. So what is r by v? Also equal to m divided by bq. Okay, therefore this t is now equal to 2 pi m divided by bq. 2 pi m divided by bq. And this is equation 4. This is the period of revolution is called as cyclotron period. Okay, this period of revolution is also called as a cyclotron period. So T is equal to 2 pi m by bq. Okay, what is the reciprocal of this time period is called as frequency of revolution. Okay, so frequency of a revolution is given as the reciprocal of the time period. Okay, so I will take f is equal to 1 by t. So this is equal to what? Bq divided by 2 pi m. Okay, so this is equal to what? Bq divided by 2 pi m. And this is the next equation number 5. Okay, this is the number of revolutions per unit time. So what is meant by frequency f? It is the reciprocal of the period, means what? It is the number of revolutions per unit time, per second. So now angular frequency, what is the expression for the angular frequency, which is denoted as omega. So omega is equal to 2 pi times the actual frequency. We have studied in the 11th standard. So angular frequency is 2 pi times the actual frequency. So this is equal to 2 pi multiplied by bq by 2 pi m. bq divided by 2 pi m. So this 2 pi is getting cancelled. Therefore angular frequency omega is equal to what? bq divided by m. So this is another equation number 6. Now equation 4, 5 and 6. You can see that equation 4, 5 and 6. These left hand sides, namely the period of revolution, the frequency of revolution and angular frequency, does not depend on the radius of the circular path as well as the velocity. So capital T, then frequency f and angular frequency, okay, they are all independent. They are all independent of R and V. This is one very important point to be noted. Also, this factor f, which is called the frequency, and omega called the angular frequency, that is f and omega are called as gyro frequency. They are called as gyro frequency. And the same is applied in the working of the cyclotron. The next topic you are going to study in the regular class is a cyclotron, which is a device used to accelerate the positive charges. For that, the same derivation is repeated. There you are going to derive the expression for the gyro frequency, namely f and omega. Okay, so in this picture we have taken that the charged particle is moving at right angle to the magnetic field. Suppose if the particle is obliquely entering into the magnetic field, not at right angle, either acute angle or obtuse angle means. So for that, let us consider that this is a uniform magnetic field B. Okay, inside this uniform magnetic field B, the charged particle is going to enter obliquely, that is in this direction. Okay, in this direction, obliquely it is entering. So this is the velocity vector. Okay, this is a V vector. Now this V vector can be resolved into two components. Okay, so This is the angle made by the velocity vector with the field vector. Theta is the angle between v vector and the b vector. So I am going to resolve this into two components. One along the field and other one is perpendicular to the field. Okay. So along the field it is what v cos theta, and perpendicular to the field it is v sin theta. We have already studied that when the charged particle is moving along the direction of the field, experiences no force. Okay, and the other component v sin theta perpendicular to the field b experiences a maximum force. So what is going to happen here? The charged particle will not move in a definite circle. It will move in a definite circle only when it is entering perpendicular to the magnetic field. So in this case where the charged particle is obliquely entering, okay, not at right angles, means it will have two types of motions. So the motion of the charged particle is a combination of translatory motion and circular motion. So the horizontal component of the velocity has no force, is it not? So as a result, what will happen now? The charged particle will move in a helical path like this, okay. Helix is a combination of translatory and circular motion both. So when a charged particle enters perpendicular to the uniform magnetic field, the path of the particle is a perfect circle. But when it is entering at some other angle, okay, obliquely into the field, means then its path will be a helix, okay, helix. Have you understood? Fine.